is choosing the equation on curve that process, which is the Markov process. The Markov property is said that given the present state of the process, the future is independent of the past. This can be stated as follows. If Ft denotes the sigma field generated by the process up to time t, then for any s is greater or equal to 0 and less than t, Vxt is less than or equal to y, the condition Fs, equal Vxt is less than or equal to y with condition Xs. It is intuitively clear from the heuristic equation above that solution to STD should have the Markov property for a small delta given xt is equal to x, while xt plus delta depends on pt plus delta minus pt, which is independent of the past. So here is the equation u1 px equal to px is less than or equal to 1, which means the condition xs is equal to x. So next we go through to the left and left processes. This process is the continuous time of chain with states 0, 1 for qij equal to 0. Whenever I minus j, epsilon I minus j is greater than 1, is called the left and left process. Let lambda I and ui be given by lambda I equal to qi, I qi, I plus I, ui equal to qi, I minus 1. Lambda I here is equal to the growth process, while I here is equal to the death process. So next, the value lambda I must be greater or equal to 0, and I must be greater or equal to 0 are respectively the birth rate and the death rate. We see that pi equal to lambda I plus pi, I plus 1 is equal to lambda I over lambda I plus ui equal to 1 minus pi minus 1.
Okay, what is both in that process? If the Markov chain for diagram look like this, okay, that start from 0 and go to the sum of finite number of n, and if you are at a middle state, critical state in middle, let's say I, and the next will either go to the right or up to about 1 unit, or left down by 1 unit, or you are will stay here where you are, and this happens in the following transition probability. So here is a qi function of this state, here as qi, and this one as the remaining 1 minus pi and qi. Okay, so this is like a different type of animal population. The animal get born and they die. Okay, the assumption here is that at any point in time, either one animal get born or one die or nothing happens. So there are no multiple deaths and births at the same time. Okay. There are many practical applications that apply for first level model.
An example of Markov chain that is supermarket counter where the state presented the number of customers in queue. A customer arrived and the queue increases by 1. Customer leave and the queue decreases by 1. Or nothing happened and the queue stayed as it is. Now, in this supermarket example, the P and the Q are taken to be the same across the state. There is easier shortcut that applies to both and that processes, and it based on the frequency integrations that we have discussed. To see this, let's draw a line between somewhere in the middle of this chain and focus on the transition between the left parts and the right parts of the two adjacents. Assume that the line cuts through the middle of two adjacent states I and I plus 1 like here, and you zoom here, and this is the picture of what you have. So what is the chain going to do? Let's say it's set on the left, it's going to move around here, and at some point it makes a transition to other side, going here. And that is a transition from I to I plus 1. And now when it's on the right side, it's going to move around as well. And then at one point, we will come back to that part again. And this is a transition from I plus 1 to I, and so on and so forth. Now there is a certain balance that must be obeyed here. The number of upward transitions through this line cannot be very different from the number of downward transitions from this line. Because if we cross this way, then in order to cross again this way, you will have to first cross down the other way. You cannot go up 100 times here in that direction and go down here 50 times. If you have gone up 100 times, it means that you have gone down 99, 100 or 101, but nothing than that. So the long-term frequency with which transitions of this kind occur has to be the same as the long-term frequency that transition of that kind occur. Or in this diagram, the frequency of that kind has to be the same as the frequency of that kind. So what are these frequencies? We discussed that before. The fraction of times at which transition of this kind are observed is the fraction of time that we happen to be at the state which is pi of I. Times that we are in that state, the fraction of time that transitions of that time happen is p of I. So the overall frequency will be pi I times p of I. And with the same argument, this is the frequency with which transitions of the time are observed, pi I plus 1 times qi plus 1. Since these two frequencies are the same, we get an equation that relates pi of I to pi of I plus 1. So this is the frequency that we observe here of this transition. And these are the frequencies of this transition. And they have to be equal. This has a nice form because it gives us equation. If you do pi I, you can calculate pi I plus 1 as such. So it's a system configuration that is easier to solve than the original system of linear equation which we presented before for a general Markov chip. But how do we get started? If we know pi of 0, then we can use it to find pi of 1. This to actually use the extra normalization condition that the sum of all the pi j has to be equal to 1. After we use that normalization condition, then we can find all the pi by first solving for pi of 0. How? This can be written pi 0 plus pi 1, which is pi 0 times p0 over q1 plus pi of 2, which is pi of 1 times p1 over q2, pi of 0 times p0 times p1 over q1 times q2, which is pi 2 plus etc. equals to 1. This equation allows us to find pi of 0. That's all. Thank you.